All right, let me try another one here for you, and a really tough one here. It's chapter 30, number 43. And I thought I would better give this one a try because I wanted to explain something here that this has to do with the magnetism of matter. And in fact, 43, 45 each have magnetism of matter. And they kind of fit with the one I just did earlier, number 39, where this is not going to be on the exam. This material, I would say, let's see, I guess it's section 6 of the Survey book and section 7 of the OpenStax book. When we start getting into the magnetization of matter, I think it's good for you to see it. And so I talked very little about it in class, and I find a few problems here. But really, this is kind of the transition between this class, which I'll call your first class on magnetism, and your next class on magnetism. And so it's hard enough here this first semester just trying to get you to understand the magnetism of free space, let alone the magnetism when you have materials present. So you should be introduced to it, and I think it'll serve you well to try to work hard on these problems, but don't stress about them because magnetism with matter will not be on the test. In fact, the OpenStax, like I said, is in section 7, and the Survey at section 6. But if you look closely at the OpenStax, you'll see that he puts an asterisk on it, and then that's kind of his sign to saying, okay, this is just, maybe you'll do it, maybe you won't. It's a little beyond the level of this class, but I think it's a good bridge. So I'm going to say it again. I think you should work on these problems. I think you should definitely study this solution, but also at the same time, you should not study it for the exam. You shouldn't stress over it, but you should keep it in the back of your mind because this will be important and be the main topic as you take your next class on magnetism. And so when you transfer, and so for most of you, that's probably next fall when you take your next electricity and magnetism level course, and you do the magnetism that has material present. So again, that's what this 43 and 45 is all about. And in fact, they use what's called the Bohr magneton, which is the magnetic moment from an electron. So there are two other problems, 65 and 66, that have a charged sphere that is rotating, and you have to calculate that magnetic moment or magnetic dipole moment, I believe, in both cases. I should go back and look at that. But something along those lines. And so, again, so I would put 65 and 66 together with that, although the mathematics you do has nothing to do with the material of matter. So you should be able to do 65 and 66 pretty well, although they are hard. But they're really not magnetism of matter. But it's the getting to you to see how an electron is. And so let me just, start here with 43 and say, okay, what's going on here? Because it says this. It says at saturation, that is when nearly all of the atoms have their magnetic moments aligned in the magnetic field in a sample of iron, it can be as high as 2 Teslas. And so what they're saying here is if you have a piece of iron, let's say I have an iron bar here, we know that the magnetism comes from moving charges. We know that was our fundamental piece of physics in chapter 29 and then carried into 30, that all of our magnetism comes from moving charges. But that doesn't mean our moving charges have to be connected to a battery. So they could just be coming from the orbiting of an electron in an atom, but it could also come from the electron spinning. And so the electron revolves and it spins. And it turns out that a lot of it actually comes from the spin. And then this one's going to contribute all of it to the spin. And so how much magnetism you get from just the spin alone is what is called a Bohr magneton. And again, that's what 65 and 66 are trying to do, get you a sphere, make it uniformly charged, and spin it, and say, okay, what would you get? And you would get a magnetic moment to it. All right, so this one is saying, though, that so if you took all of these iron atoms and get them saturated, that is the most you would ever get aligned, you would get a field strength of about 2 Tesla. And so what this is really saying here is that the magnetism comes from where? So in a very strong magnet, in an iron magnet that had a value of 2 Teslas, it's all coming from the alignment of the spins. And that's what this is after. And it says, watch this, it says, if each electron contributes to the magnetic moment of, and so it says 9.27 times 10 to the negative 24 amps meter squared. That's the unit for a magnetic moment. This is called 1 Bohr magneton. How many electrons per atom are contributing to this saturation field of iron? And so I'm trying to remember, where's iron on the periodic table? I want to say 26. Do I have a periodic table I can look up real quick? I think I might. So let's see. Good. Where is iron on here? Fe. Yeah, there it is, 26. Okay, good. So my memory was serving me well. And here's what they're trying to say is obviously the most of any you could ever line up is 26 of them. But there's other reasons like the Pauli exclusion principle that would say you're not going to get all 26 of them to line up. And in fact, how many do you get lined up? Excuse me, we can answer sort of here by this question here. And so it is saying here that if you take this number, which we often give the symbol mu sub b, a Bohr magneton, and we say, okay, so take this number, a Bohr magneton, that's how much, again, magnetic moment you get from just one electron. Then how many of them per each atom would we actually have when we're going to get a field this strong? Okay, so I'm going to take this number, mu sub b, and then multiply it by, say, x. And this x is going to be my symbol of saying, now, how many electrons are lining up? Like I said, it could never be more than 26, because that's the most I have, is 26. Okay. But it is much, much smaller than that. And knowing a little chemistry and knowing about the d orbitals and the Pauli exclusion principle, so those of you gone through chemistry know that we're probably looking at a most of 2. 3 on the outside, but probably in that neighborhood of 1.5, maybe to 2 because of other factors. All right. So, but that's the number I would like to find. That's what this question really is asking. How many? So, that number, x times a Bohr magneton, would tell me what kind of magnetic moment I get from that one atom. So if I then multiply this by the concentration, let me call that N, how many atoms are there per volume, I would get what is called the magnetization per volume. And sadly, this is the part where I think the author could have done a little better job, and myself too, I'll admit it. I just kind of brushed on this real quickly because, like I said, this is really transitioning to the next level of your classes. So if this doesn't completely make sense, don't stress. This is not on the exam, but it's good to see this. So this, like I said, is the magnetization per volume. And there's a connection. The permeability of free space, permeability of free space times the magnetization volume does give you the strength of the field. And that's the part that you may not be familiar with that equation. The author doesn't bluntly give it that way. He kind of describes it in words. But knowing that, then, we can do this. We can say this is the total field. Okay, so we'll take it by the permeability of free space, and then the number of atoms per volume, then the number of electrons per atom that are lining up, and then the magnetic moment we get for one individual electron. And then we can see what number we get, because we know this. This is going to be the 2 Teslas. I'll just put a 2. This is the mu naught, the permeability of free space. So this is 4 pi times 10 to the negative 7. This is what they say is the concentration. And I think I need to go back and look at this. I think they said 8.50 times 10 to the 28th atoms per volume. Let me look here. Yeah, per cubic meter. Good. And then this X is what I'd like to find. And then this Bohr magneton, that's the magnetization from 1 electron. And that's really probably the most important part, I think, for you, is not so much this calculation, but just kind of this understanding, an understanding that you can take with you to the next level and say, okay, how do we get our magnetization for materials? Because we're learning very well, or hopefully you're learning it well, the magnetization comes from moving charges, and we're having things like loops of current and squares and rectangles of currents, and then currents next to currents, and see how they interact. And so we're doing all this magnetism in free space, you know, but we haven't really been asking, okay, what would happen if there was, you know, a piece of iron in between them, or a piece of cobalt in between them, a piece of nickel, or maybe something that's not magnetized, like a piece of aluminum in between them, you know. And why are those in the d orbitals magnetized or magnetic, and the strong magnets, the rare earth magnets, the f orbitals are, whereas the p stuff like aluminum is not, and magnesium is not. But that's a fun discussion about material science and chemistry. All right, but let me grab my calculator here. So if I go 2 divided by 4, and also divide that by pi, and also divide that by 1 times 10 to the negative 7, and also divide that by 8.5 times 10 to the 28th, and then also divide that by 9.27 times 10 to the negative 24, I get a number around 2.02. And so that's my original guess, just based upon what I know about iron and being in the d orbitals, and that 2 of them are going to contribute. So those last 2 in the d orbital do not pair up and flip. They stay up, and so they all add. The other ones are all paired up in groups. So the first 24 are equal and opposite and cancel each other, but the 25th and the 26th electrons are actually in different orbitals, in the d orbitals, and they are aligned together, and they add up to the magnetism. All right, well, again, hopefully that relieves a little bit of stress, but it's not much of a calculation, but it is a lot of the understanding of materials. Again, not on the test, but good to go through this and see it.